Okay, good morning, guys. So we are gonna go ahead and continue with correlation. And for today, we are gonna do correlation definition again and properties of correlation. And then we'll do hypothesis testing involving correlation. And after that, we are gonna do linear regression. Okay, we are gonna do linear regression, and then we will predict values using our linear regression model. And that's kind of like the overview of what I'm planning to do for the day. So what is correlation? Correlation is the association between two variables, or the relation between two variables. We have talked about it in the last class. Again, this is going to be a repetition. So correlation is the association or relationship between two variables. The correlation is measured by R, okay? Correlation is measured by R. It's called the correlation coefficient. It's also known as Pearson correlation coefficient, and it was invented by somebody. So it's named after his name, Pearson. So this is the formula for correlation. R is equal to 1 over n minus 1. N is the sample size. And you sum over each values of x, okay? So x minus x bar divided by standard deviation of the x's, y minus y bar divided by the standard deviation of the y values. And now this, by the way, is normalized value or standardized value. This and this, as you can see, it kind of looks like z-scores, right? Okay, you normalize or standardize values. Remember, z is equal to x minus x bar divided by s. That's the formula we used. So now we apply this formula twice, once for the x values and once for the y values. Now, let's go ahead and talk about some of the things, properties of linear correlation. Okay. One thing before I jump to the next topics, which is characteristics of linear correlation, I kind of want to emphasize the fact that correlation does not mean that one thing causes the other. Okay. What we say in statistics, correlation does not mean causation. Okay. As I told you before, that during the winter, you get flu and cold, right? That doesn't mean that the cold temperature causes you to get the flu and the fever, or, you know, whatever other things that come with the cold season. But rather what happens is that during the cold weather, certain bacteria happens to be present in the environment, and that's what's causing the cold and the flu. All right. Similarly, during the spring season, you tend to have allergy, right? Okay, you tend to have allergy during the spring season. That doesn't mean that the spring temperature or spring weather in and of itself causes you to have allergy, but rather the presence of pollen in the environment during that period causes the allergy. So one thing I kind of want to emphasize here is that please do not make conclusions based on correlation. Okay, I meant to say causation. Don't think that two variables or two things are correlated to each other does not necessarily mean that one causes the other. So, which said in another way is that correlation does not mean causation. Okay, so keep that thing in mind. All you can say is that these two things, okay, two variables that you're comparing, there is some sort of association or relation between them. Okay, and that association or relation is measured by the Pearson correlation coefficient using the formula that I just showed you a few minutes ago. Now, when we are talking about sales tax, okay, you spend $100. Let's say your sales tax is 8%, you pay $8. If you spend $200, you pay twice as much sales tax. If you spend $300, you pay 3 times as much sales tax compared to this value. Now, this is a perfect correlation where correlation R is equal to 1, perfectly positive correlation. All right. This is a perfectly positive correlation. Okay. Now, this correlation could be negative as well. Okay. That means if one thing goes up, the other thing goes down. If one variable increases, the other variable decreases. Okay. Let's say the number of hours you work, if it increase, oh well, that's, yeah, sure, I can do it that way. The number of hours you work and the amount of leisure time that you have, there is a correlation between the two, but it's kind of opposite. If you work more, you have less time for leisure. On the other hand, if you work less, you have more time for leisure. See? Or in the world of business and economics, you can think of it another way, price. If the price of a commodity increases, the demand for it decreases. Okay? If the price of an item increases, the demand for it decreases. So they are negatively correlated. Okay? Positive correlated, negatively correlated. So hold on one second. I'm seeing something here. What is it saying? Who can see what you share recording? Oh. Okay. Now, some properties, there are 5 of them I talk about here. So one is a correlation coefficient. It's a value between -1 and +1. It cannot be more than 1 or it cannot be less than -1. Okay. Correlation values, Pearson linear correlation values are between +1 and -1. Then number 2, when R is -1, we have perfectly negative correlation. And when R is +1, we have perfectly positive correlation. And when R is 0, there is no linear correlation between the two variables. When R is 0, there is no linear correlation. However, there may be non-linear correlation between the variables. Okay. So keep that in mind. When I say linear correlation, that means it's a correlation where it looks like a straight line, like this or like that. So this is positive correlation, you can think. This is negative correlation, you can think. So in nonlinear, R is 0 means no linear correlation, means it could be nonlinear or there is actually no correlation. Then the third rule, which is kind of rule of thumb, if R is greater than 0.8, if R correlation coefficient is greater than 0.8, it's called strong positive correlation. When R is less than 0.8, I mean less than -0.8, then it is considered strong negative correlation. So strong positive correlation and strong negative correlation. Then the next thing is linear correlation coefficient may be significantly affected by the presence of outliers. Okay. if you have a data point that is outlier, that could significantly impact the linear correlation. Okay, so for instance, let's say you are thinking of home prices. Okay, there is a correlation between the square footage. Okay, by that I mean how big the home is, the home itself, not the entire lot. Let's say, for simplicity, there is a correlation between the square footage, that means how many square foot the area, livable area in the home is, okay, and the price. Okay, there is a correlation between livable area or living area in a home and the price, which is typically measured by square footage. Okay, square foot. So let's say when we say a home is 1,500 square foot or 1,800 square foot or 2,500 square foot, okay, the bigger the square footage, the higher the price. So now there is a linear correlation, but what if you have one home that has some historic value? Okay, let's say in the community there is one home that has some historic value, even though it's, let's say, 1,500 square foot home, but its price is, let's say, $2 million, whereas the price of the other homes are like, let's say, in the 500K range for this square footage. Now, this may be considered an outlier, okay, and this may impact the linear correlation. So what you may want to do is kind of purge the data, kind of cleanse the data, okay, before you find linear correlation. If you have one or two extreme data points that might give you linear correlation that is not reflective of the reality, but rather is biased because of the presence of one or two outliers. So make sure that you observe the data either visually or by using some sort of statistical tools to ensure that there are no extreme values or there are no outliers, so that you get a good measure of the linear correlation. The last one is this: the values of R is not affected by scaling of the data set. That means if you change the units, okay, now let's say here we are measuring by square footage and here we are measuring the price by dollar. What if we change the square footage by square meters? You could do that, okay? Instead of using square foot, you're going to use square meter. And the price, we still keep it in dollars. That should not change the linear correlation. Or we change the, we keep the square footage same, but then we change the dollar to, let's say, euro. Okay, we keep the square footage the same, but change the dollar to euro. That should not change the linear correlation. Or we can even change both of these. Let's say we change the square footage to square meters and then change the dollar to, let's say, taka. Taka is the currency of Bangladesh, okay? So we change it to taka. So that should not make a difference. So these are the properties or attributes of linear correlation, okay? So to summarize, linear correlation describes the association or relation between two variables. And that association or the strength of that association or relation is measured by a linear correlation coefficient, also known as Pearson linear correlation coefficient, R, okay? And R is defined the way I showed you right here. Okay, right here, you can see this is how R is defined. Now let's go back. Okay, now R has a range between -1 and +1. It cannot be more than 1, nor can it be less than 1. R0 means no linear correlation, but there could be nonlinear correlation, which we don't talk about in this class. R +1 means perfect positive correlation. R -1 means perfect negative correlation. R greater than 0.8 means it is strong positive correlation. R less than -0.8 means is strong negative correlation. Linear correlation coefficient R may be affected by the presence of outliers. Okay, that means extreme data points. Remember, outliers are extreme data points. It could be very large compared to the rest of the data, or it could be very small compared to the rest of the data. So outlier could be big or small. Don't necessarily assume that it's a big data point compared to the rest. It could be small too. And the change of units will not affect the Pearson linear correlation R because the values are normalized or standardized in the formula. Okay, so that concludes the discussion of linear correlation and its definition. Now let's go ahead and do some problems. Now for this one, by the way, you just need to use, I use the calculator, but you can go online and find linear correlation coefficient calculator or search for Pearson linear correlation calculation. You'll find tools where you can enter these data points. So the first data point is your X and the second data point is your Y, X, Y. By the way, order doesn't matter technically. In the Pearson linear correlation, okay? If you write the x's as y's and y's as x's, it doesn't matter. The correlation is not affected by the order of the bivariate data. Bivariate data, which is a fancy name for XY pairs, okay? It's a fancy name for XY pairs. That's what it is. Okay, so let me look at my calculator, see if I have these data points. Then I could find that. So for these problems, we ask you to find the correlation coefficient R, okay? I see 20, 10, 35, okay. And is there 200 somewhere? Yeah, 200 there too. And it goes all the way down to 55, good. At least I have one column data. Then let's go ahead and fill in the other one, 10, 5, 5, 10. Oops, let's clear it up first. Yeah, 10, 5, 5. Oops. Sorry, made a mistake. Hold on 1 second. It's not 10, 5, 5. It's 3, 0, 5, 5. 3, 0, 5, 5. Then 40, 20, 10, 40, 20, 10, then 13, 7, 20, 13, 7, and 20. So what I have done in my calculator, I have put the data points in two columns. Okay, one of the columns is L4, another column is L5. So if you have the TI calculator, you can enter them in any two columns you want. It doesn't matter. I put them in L4 and L5. Then what I'm gonna do, I'm gonna go back to stats, and then let's see, L4, L5, hold on for a second. L4. Okay. I'll have to go to lean reg. Okay, lean reg t-test. L4, L5, and calculate. Okay. I'll tell you what I'm doing, okay? So please give me a second. So this gives me R value of 0.96 and R square is 0.92. R square is actually the value that we use to measure the strength of the linear correlation, okay? So technically, indirectly, R is being used, right? So R is the linear correlation coefficient, okay, which we found 0.96. Now, how did I find it? So let me tell you again, if you're using the TI calculator, this is what you should be doing. You go to stat, then you go to tests. So, okay, on the top, you select tests. Then hit the up arrow key. That way you don't have to scroll through everything. Hit the up arrow key and you'll see on selection F dot, it has lean reg t-test. Lean reg t-test. It has lean reg t-test. If you enter that, so you put your X list and Y list. X's are in L4, that's where I put them. And Y's are in L5, so I put them there. And then you go to the bottom of the screen and you should see calculate. Okay, and if you hit enter, then if you scroll down, you have to scroll down to find the R value, which is 0.96, and R square value, which is 0.92. Now, this is the linear correlation coefficient. R is equal to 0.96 for this data set, okay? And as I said, R square is used to measure the strength of the correlation, because remember, R could be positive or negative, right? So we use the R square to get a positive value, all right? Which gives us a positive value that kind of gives you a sense of the strength of the correlation. The bigger the value R square is, the greater the strength is. Any question, anybody, that I could answer for you, please? Anyone has any question? No questions? Everybody okay? Looks like everybody is okay, no question. All right, so in the second question, so I'll write down these values because I will need it next time. So 0.96 for this one. So for the next one, so the first one was about the amount spent and the tips, right? Okay, tips for different amounts spent. And the following the number of hours a group of statistics students studied for a test, okay, corresponding scores, okay? So the number of hours they studied and their corresponding scores. So X, Y pair again. X is the number of hours you studied and Y is the score that you received out of 100. So let me go ahead and enter these data points again. So 5, 3, 8, 12, 5, 3, 8, 12, 15, 8, 9, 15, 8, 9, 10, 11, 13, 10, 11, 13. So I have put the X values in column 1. Now I'm going to put the corresponding Y values in column 2. 72, 50, and 80. 72, 50, and 80, and then 88, 90, 80, 88, 90, 80, then 90, 85, 82, 90, 85, 82, and then the final number is 95. Okay, so I have entered these data points, in L1 and L2. By the way, guys, if you search for tools online, there are several tools you'll easily get. You can just plug it in these values, X and Y's. They will tell you exactly how to plug it in, maybe comma separated, or they will give you two columns where you put the X's and Y's, and then calculate, you'll get these values. So this is no rocket science. So I put my data points in L1 and L2 in TI calculator. So now I go back to stats, then go to tests and up arrow, lean reg t-test. And now I have to change it to L1 and L2. Second one is gonna give me L1, and second two is gonna give me L2, and calculate. Okay, if I do the calculation, I get R is equal to 0.86 and R square is equal to 0.74. Okay, I didn't round it, I just took it as it is. So this gives us the strength of the association. This is the actual value of the linear correlation. One gives you the strength of the association, the other one gives you the strength of the value, strength of the association. So that's what it is. So I'll need both of these values, 0.86, this one. Now, any question on this? This is the value and this is the strength, okay? Anybody, any questions before I move on to the next few things? Alicia, any question?
No question.
Okay. Now we are going to do a mini hypothesis testing using linear correlation. So basically we are going to do a hypothesis testing where we are going to check whether there is statistically significant linear correlation between two variables. We are going to check whether there is statistically significant correlation or linear correlation between two variables. And the process for doing hypothesis testing using linear correlation is pretty much the same that we did before. Requirements. So make sure that the data does not have outliers. As you can see, outliers. If you have outliers, that's gonna change the correlation coefficient in a meaningful way so that it does not reflect the reality. So make sure that your data does not have a historical home with a small square footage but skyrocketed value. Okay, this is just one example I am giving you. Make sure outliers are excluded. And the bivariate data such as XY pairs has normal distribution. This means that for any fixed value of X, possible Y values are normally distributed. Okay. So these are the assumptions, approximate, bell shape, and outliers excluded. The null hypothesis is that there is no linear correlation. This is not P, by the way. This is the Greek letter rho. It's spelled R-H-O, rho. This kind of looks like a P, but this is what the shape of it. This is rho. Rho is 0, meaning what? There is no linear correlation. And whereas alternative hypothesis is rho is not equal to 0. That means there is linear correlation. So that's what the thing. Rho is equal to 0, meaning that there is no linear correlation between the two variables in question. On the other hand, rho is not equal to 0, meaning that there is. Okay, so it's kind of like contradictory looking. So rho 0 means you're kind of thinking, oh, no linear correlation. Rho 0 means no linear correlation, I guess. Yeah, I guess that's how you could be thinking. Rho not 0 means there is linear correlation. This is always a two-tailed test, okay? And the test statistic is nothing but the linear correlation coefficient you got from the sample data. That's why I saved the other two values, okay? We are going to be using that. The test statistic is the linear correlation coefficient, and the critical regions determined by Pearson's correlation coefficient are table. And that's the table you guys have, and I'm gonna tell you where it is. If you have that file, the formula sheet that I gave you, please open it. This will help you, okay? I want you to look at the formula sheet when I am working on the problem. It's pretty easy, by the way. Pearson linear correlation coefficient, okay? So Pearson correlation coefficient are table for different sample sizes. And the conclusion, based on the test statistic, you make the conclusion, okay? If the absolute value of R is greater than the critical value, we reject the null hypothesis, else we fail to reject, or we do not reject the null hypothesis. So these are the two things. One is you reject the null hypothesis if the absolute value is greater than the critical value. And we do not reject the null hypothesis if the absolute value is less than the critical value. And that's the process. Now let me do a couple of problems involving this, okay? This way you'll get a sense of how to apply this process. So let's do, okay. This is the same data I used, right? I just wanted to make sure. Yeah. Oh, I actually did the problem here. Okay. So first, this is the same data, by the way. The following are the tips for different amounts spent at a local restaurant. The bivariate data is given as a pair of data points. So if somebody spent $20, they gave $3 tip. Somebody spent $55, was in a good mood, gave $20 tip, okay? And so on and so forth. So assumption-wise, we just look at these data points. Is there any data point that looks like unusual? Somebody spent $100, but gave like $200 tip. Is there anything unusual like that? The answer is no, okay? There is nothing there. So we need to test at 0.05 significance level that there is linear correlation, okay? At 0.05 significance level, you need to show that rho is not equal to 0, meaning that there is correlation. So again, normality, we kind of have to assume it. We don't show the normality, or we don't apply any normality test, okay? We don't apply any normality test because that would complicate things. That's in and of itself is a topic, okay? Testing for normality in the data set. We just assume that, we just make simple assumption that it is normal, normality condition is met, and also we assume that there is no outlier in the data set. Your null hypothesis is that rho is equal to 0, and the alternative is rho is not equal to 0. Your test statistic is 0.96, is R star. Remember, we found that R value of 0.96 for the first data set, which is exactly this data set, R value of 0.96. So critical value for R. So now critical values of R, for that one, you have to, so let me open the formula sheet myself first. It's in the page number 3, table A6, okay? Page number 3, okay? On the right side of the page, table A6, A is in apple, -6. It gives you critical values of the Pearson correlation coefficient R. So they tell you, if you look at alpha is equal to 0.05, and they also give you for alpha is equal to 0.01. Okay, that means significance level 0.05 and significance level 0.01, or 5% significance or 1% significance. Now, the degrees of freedom here is kind of like interesting. You have 10 pairs of data, so you have to subtract 2, okay? Because we are dealing with 2 variables, x and y. So degrees of freedom is 10 minus 2, 8. Unlike the last time where the degrees of freedom was n minus 1. In this case, degrees of freedom is n minus 2. This is not here. This is not for correlation. This is for hypothesis testing and confidence interval. Is for hypothesis testing and confidence interval. That's why you use n minus 1 as degrees of freedom. This is also hypothesis testing. By that I mean hypothesis testing for proportion, mean, and standard deviation. That's why you'd be using this. For correlation, you'll be using n minus 2, which is 10 minus 2, 8. So now if you look at the degrees of freedom column, so the way the table is structured is this: n alpha is equal to 0.05 and alpha is equal to 0.01, and n goes from 4, 5, 6, and it goes. So if you look at 6, 7, 8, so that's our interest. And if you look at the corresponding value for this, you're going to get 0.707. This is what we have. This is the critical value for R, and this is the test statistic. Now, absolute value of 0.96 is 0.96, which is obviously greater than 0.707. So, since the test statistic is greater than the critical value of R, we do reject the null hypothesis that rho is equal to 0. Since the test statistic is greater than the critical value 0.7, okay, 0.96 is greater than 0.707, so we will reject the null hypothesis that rho is 0, which means that there is no linear correlation between these 2 variables. We reject that assumption. That means we are claiming that there is linear correlation between these 2 variables. There is linear correlation between these 2 variables. So this is the step that you are going to follow in order to do hypothesis testing involving linear correlation coefficient. Is this process making sense? Is everybody okay with the process? Anyone not sure how to do it, or any question? Anyone? Please do not hesitate to ask me questions if you have any. You can clarify your concerns and get answer to your questions. Please do make sure that you ask me questions if you have any. Anybody? Once more, anyone? Any question? Okay. Next, we are going to do another hypothesis testing involving rho. So it's exactly the same thing, but this time I use the second data set from the table. So from the last one, see this data set, is this. Okay, so let's go ahead and work on that. Which is this one. The following are the number of hours a group of statistics students studied for a test and the corresponding scores. So these are the data points. At 0.05 significance level, test the claim that rho is not zero. That means there is linear correlation between number of hours a student study and the corresponding score in the midterm or in the exam. So the number of hours a student studies and the corresponding score on the test. So we are going to go through the steps. Step number 1 is that, is there an outlier? Obviously, there is no outlier here. Nothing crazy like somebody studied 0 hours and got 100 points. Or somebody studied 100 hours and got 0 points. Some weird relation, no, nothing like that. So that is true. And we can also assume that the data points are normal coming from a distribution that is normal. Okay, we are assuming that these data points are coming from distribution that is normal. Now, having said that, no outliers, and normality condition satisfied. That means normal. Step number 2, your null hypothesis H naught is rho is equal to 0, and your H sub A is equal to, oops, not equal to, colon, rho is not equal to 0. That's number 2. Number 3, your test statistic R star, which is, by the way, we found to be 0.86. And this is something you have to calculate in the exam. So if I give you a problem like this, you just have to basically do the calculation for R. You need to find the R. You need to know how to either use your calculator, okay, or go online and search for Pearson. So use the word Pearson, okay, when you're searching for linear correlation, because there are other correlations too. So I want to make sure that you do the right correlation. Pearson linear correlation. Okay, Pearson linear correlation. Make sure that you search for it. So R star is 0.86. Now, how many data sets, data pairs do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So n is equal to 10. So degrees of freedom is going to be n minus 2, which is 10 minus 2. That is also 8. And we have the same significance level, okay? So by looking at the table, Pearson correlation table, for alpha is equal to 0.05 and degrees of freedom df is equal to 8, we get the same value, R, critical value for R, 0.707. Okay. Now step number 5, where we make conclusion. So absolute value of R star, right? Which is absolute value of 0.86, that is equal to 0.86, which is greater than 0.707, okay? Therefore, we reject the null hypothesis. We reject the null hypothesis. What is the null hypothesis? That rho is equal to 0, meaning that there is no linear correlation. Rho is 0 means there is no linear correlation. Okay, That's how you do it. Now, what if I change this to alpha is equal to 0.01 instead of 0.5? In that case, your R is going to change. This R is going to change. This R from the table, I can say is 0.834. Okay. So at 0.01 significance level, R is 0.834, but my R star or test statistic is still 0.86, right? 0.86 is still greater than 0.834, right? Therefore, we would still reject the null hypothesis that there is no linear correlation between the two variables. So at 0.05 significance level, which is in the problem, we will reject the null hypothesis. And even 0.01 significance level, we will reject the null hypothesis. In either case, we would reject the null hypothesis. Okay. Now, what if my R star instead of 0.86, let's say it's 0.78, let's say. In that case, what will happen? So this is going to be replaced by 0.78. So this is still bigger than this. Therefore, we will reject the null hypothesis at 0.05 significance level. However, at 0.01 significance level, if this is 0.78, obviously this is less than 0.834, we will not reject the null hypothesis in the 0.01 significance level if my test statistic were 0.78. So this is the whole story about the hypothesis testing. Okay, the hypothesis testing involving linear correlation. So we covered everything about linear correlation. We defined linear correlation. We have talked about, so this is the summary of what I did for linear correlation. So we define linear correlation definition. We talked about the properties of linear correlation. Then important fact, remember, correlation does not imply causation. That's a typical mistake people make, imply causation. That means just because two variables have correlation does not mean that one causes the other or vice versa. Example, you should be thinking about allergy, springtime allergy caused by pollen as opposed to the weather, temperature itself, or the wintertime cold and flu caused by some bacteria rather than the actual cold temperature or actual lower temperature. Because that bacteria happens to exist only in certain temperature, and that temperature happens to show up in winter time. Okay, so that's correlation does not imply causation. And step number 4, we talked about hypothesis testing involving linear correlation coefficient R. So these are the 4 things that we talked about. So that concludes our discussion of linear correlation. All right. It concludes the discussion of linear correlation. Okay, any question, anybody, before I move on to the next topic? Anybody, any question, anyone? One last chance. No questions? No questions, everybody okay? All right. All right, so guys, just to remind you again, this week and the next week, these are the 2 weeks that we will have our regular classes. So today is May 3rd, Monday. So we are going to have another class on May 5th, Wednesday, okay? And then next class, May 10th, which is Monday, and the last class for the regular semester for regular instructions before the final exams is May 12th. So we are going to have regular class this week, regular class next week, and then on the week of 17th is going to be finals week. So we are going to have our final exam during that week. Okay, and I'll give you the details. It's going to be the same structure and everything. Okay, so during the last week, I'm going to just have you take the final. That's it. Any question about the logistics of the remaining of the semester? Anybody? Everybody okay? All right. So let's go ahead and get started with the next topic. By the way, I'll be sending an email about it too. So our final exam week is the week of 17th. So on the 17th and 19th, I'll probably give you a couple of days to work on the midterm, on the final exam. So you'll have Monday and Wednesday, both days to work on the final. I'll probably give you even the Tuesday. So it should be plenty of time for you to work on the final exam, and it will be structured exactly the way the midterms were structured. To study for the final, I'll give you a set of review problems, okay? And I will also hold a review session before the final, like the way I did for the midterms. So before the final exam, I will hold a review session, which probably will be over the weekend before the finals week. All right. And you can ask me questions. I will open. So one key announcement here. I'll open all the past homeworks. Okay. All the past homework that I have given you, and you can work on it. If you missed anything.
Thank you.
You're welcome. So if you missed anything, this is your opportunity to catch up. And it will be open until May 16th. Okay. On the 17th, we are going to have our final exam, so I will not keep it open. On the 17th, it will be all closed. But May 16th, until May 16th, you'll be able to work on the previous homework. So if anyone missed anything, this is your opportunity to catch up. Okay. Next topic is linear regression. I kind of want to give you an example. And this is kind of interesting. So far, you have seen things like this. You go to a store and you spend $100. Let's say your sales tax is 10%. I'm just going to keep it a nice number. So you pay $10 in sales tax. Okay. You spend $100 and you pay taxes T. You spend $200, you pay $20 tax. So you spend $300, you pay $30 in taxes. How do you calculate this number? There is an easy formula for it. Y is equal to mx. Remember, equation of a straight line, y is equal to mx plus b, intermediate algebra that you have taken. So in our specific example, if y is the tax amount, sales tax, and x is the amount spent, okay, then this equation becomes y is equal to sales tax is 10%. M is the rate of change, how the tax changes, okay? So rate of change is fixed here, which is 10% or 0.1. 0.1 is 10%. Times x plus b. B is the y-intercept, which is going to be 0. Why is it 0? Because if you don't spend any money, that means if your x is equal to 0, you pay no sales tax. Your Y is also 0, right? If you don't spend money, you will not be paying sales tax. So your equation becomes Y is equal to 0.1 times X. This is the equation. And this is exactly how you're doing this calculation. Look, what is your sales tax? If you spend $100, what is your Y? It's going to be 0.1 times 100, which is what? 10. If you spend $200, what is your Y? 0.1 times 200, which is what? 20. What if you spend $300? It is 0.1 times 300, which is what? 30. As you can see how these numbers change. This is exactly what we have got here for the corresponding X values. This is what we call a deterministic world. Deterministic world. Okay? This is what math is like to you until you have started to take statistics. In the world of mathematics that young people learn, you see everything very deterministic way, or more of a binary way, black or white, either this or that. There is no shades of gray. Okay? Like, for example, if you spend $100, you must have to pay $10 tip. You don't have a room for leeway. You cannot say, oh yeah, I kind of don't feel like giving $10. I'll give you $5 or $3, or I won't pay you taxes. That doesn't work like that. It's very strict. Okay? That means it is deterministic. Okay? Which follows a certain mathematical formula. Okay? Which follows a certain mathematical formula or equation, which you all are very comfortable with. And that's exactly what Y is equal to mx plus b, equation of a straight line or a linear equation. However, things get interesting. What if it's not so deterministic? What if it is indeterministic? What if things are indeterministic? And my favorite example, or examples rather, are this one, sales tax and tips you pay at a restaurant. Tips you pay at a restaurant. Now, when you pay tips, let's say you spend $100, expectation is that you'd pay 15%. But do you pay $15 exactly? The answer is almost always no. Okay? So somebody may spend $100 and in a good mood may pay $30. Somebody may spend $200 and in a bad mood may pay $10 in tips. Somebody may spend $300 and pay $40 in tips. And if you compare this with that, there is a sharp distinction. Here, all of these numbers are deterministic, meaning it's fixed, you cannot change it. Whereas here, all of these numbers are indeterministic, or I would use the word random / uncertain. There is a degree of uncertainty associated with this. There is a degree of uncertainty associated with it. And interestingly, the real world is more like this than this. The real world is more like this than this. Because in real world, many things follow some sort of relationship, but it's not a precise relationship. In real world, many things follow relationship, but it's not precise like the sales tax. Think. Tips is an example, right? Where the amount of tips paid depend on X, the amount spent. but it is not fixed, or there is a degree of uncertainty or variation. So instead of y is equal to mx plus b, what we do here, we had y is equal to mx plus b, which is deterministic. We use an epsilon, which is called an error term, a random error. Random error term. Okay. And the assumption is that this has a distribution which is bell-shaped with a mean of 0. Okay. It has a distribution bell-shaped, the mean of 0, and variance sigma square. And this is the difference between deterministic world and indeterministic world. And things get quite interesting in the indeterministic world. Now, let's say, let's compare these two equations, this one and this one. Okay, this one and this one. Here, you know what the slope is, 0.1. There is no hinky-pinky with that. You cannot do anything with it. It's 10%, 0.1 given. However, what is the value of m here? For simplicity, let's say there is no b. Okay, what is the value of m here? We don't know. As a matter of fact, there is no fixed value either. Think of these two scenarios. You go to a regular restaurant in Salinas, okay, just an ordinary restaurant. This m value may be close to, let's say, 12%, let's say 0.12. Okay. On the other hand, if you go to an upscale restaurant, let's say in Pebble Beach, where the golf course is, over there, you do the same kind of calculation, same kind of data collection you do. Somebody spent $100, $200, $300, and how much tips they pay. And based on that data, your M might be, let's say, 0.20. Do you see? Just for two different restaurants, depending on the location, these M values could change, right? And in linear regression, the entire job of linear regression is finding these M values for a specific data set. This is exactly what you are doing. You are finding this M value for a specific data set. Now, what does this mean graphically? This is what it means. Let's say for a restaurant in Salinas, okay, the tips, so that's your tips, and this is your dollars spent. It may look like this, okay, something like that. Now, what you try to do, you try to find a straight line that's gonna go through these data points and best fit the data set, okay? So maybe something like this will be a best fit data, all right? So this line has a slope, okay? So let's say m is equal to 0.12. On the other hand, you do similar calculations or similar data collection for Pebble Beach, and you get something like that. Both, by the way, are a straight line, and this one may be like this, and this has a slope m is equal to, let's say, 0.2. So in both of these cases, you're finding the m, that is the slope, okay? That means you're finding the slope for this data set and you're finding the slope for this data set. They're different. One does not apply to another really so much. It's very context dependent on the location of the restaurant that determines. So here you have higher slope because a lot of celebrities go there. They probably tend to tip better. Here you have ordinary people going to the restaurants and they probably give ordinary tips. Do you see? That's the big difference. And The job of regression is to find this M value. Okay, these M values for different data set. And this is what, physically what it means. If you are to visualize this data set, what you are doing, you're finding the best fit line, or the line, straight line that best fits the given data set. Now, another way of saying the same thing, more mathematically, you're trying to fit the line by finding the slopes. That's what linear regression is all about. And of course, I could give you many examples of these regression type of problems that appear in the real world. Okay, my favorite example to give you is this: self-driving cars. Okay, and now they are kind of popular, and more people are using self-driving cars. Now, self-driving cars, what it is doing is basically doing a lot of fitting like this. Behind the scenes is doing a lot of fitting like this, not linear fitting, okay, but rather non-linear fitting. Okay, self-driving car, at the core of it, is basically doing a lot of non-linear best fit lines. Okay, and based on that, they try to predict. So here is an example I'll give you. So let's say this is the M value you got, y is equal to 0.12 times x. Based on these data, how much somebody who spent $150 will pay in tips? So what you will do, you'll take y is equal to 0.12 times 150, which is, by the way, $18. Okay, is it 18? 50, yeah, $18. Based on this, somebody would give $18 tip if the person were to spend $150. On the other hand, if they were to go to this restaurant, they would pay y is equal to 0.2 times 180, which is $36 tip. Oops, did I do? Sorry, not 180, 150, which is going to be $30 tips. For spending the same amount here, they pay $30 tips. For spending the same amount here, they pay $18 tip. All right, that's what it is. Now, the interesting part is this. In a self-driving car, of course, they're doing similar calculations, but they're not coming up with a value per se. What they come up with is a probability value. So for instance, in front of a car, so let's say this is the car. In front of a car, let's say somebody is standing, a human. Okay, that's a human, my way of drawing human. So the car sees this human, takes a picture of it. There is camera in the self-driving car. It takes a picture of it, and you can think of it kind of in a very simplistic way. It's kind of trying to feed it data in a non-linear way. Okay, and at the end, instead of giving it also gives a number, by the way. At the end, it gives out a number, it spits out a number like this here, but that number would be a probability value. Let's say it could be 70% or 80% or 90%. Okay, it'll be a percentage. So it will spit out a number saying that there is a 90% chance that the object in front of me is a human being. Okay, there is a 90% chance that object in front of me is a human being. Based on this, the car's internal mechanism is going to decide, oh, there is a man or a woman in front of me, there is a human being in front of me, so I better slow down, I better press the brake. And all of these things, by the way, has to happen in a matter of split second in self-driving car or autonomous cars. All of this has to happen in a matter of split second. Otherwise, we have a problem. Houston, we have a problem. Okay. Now, here is the amazing part. All of you drive, right? You guys know what it is like driving. So if you see a human being, if you see a person in front of your car, right away, without thinking, subconsciously you press your brakes without even thinking. You don't do a mathematical analysis in your brain. Hey, let me find out the probability that is a human being. But interestingly, did you know that in a matter of split second, that when you are deciding to press your brake by seeing a human being in front of your car, it actually is doing similar kind of calculations in your brain. However, your brain is so powerful that it can do this kind of calculation in a matter of 1/10 of a second or even less. Okay, it could do this calculation in a matter of less than 1/10 of a second. That's why you don't think about it. All right. So self-driving cars are doing these kind of things all the time. And what is going under the hood is something similar to this: fitting something or finding the best fit for a certain things, for a group of things, or for a certain collection of things. I gave you a very simple example of tips and amount spent. So you can see the power of this regression. We talk about linear regression. There is non-linear regression. In the real world right now, what you see, all of you have heard of things like artificial intelligence, which is also known as machine learning. Okay, artificial intelligence, that is also known as machine learning. Machine learning models are doing exactly these kind of things, finding the best fit line. Okay, and in their case, it's not a line, it's a curved space, or what they call hyperdimension, or some multidimensional space. Okay, but in theory, in simple term, this is exactly what they're doing. You can imagine if this data were three-dimensional, then it won't be a straight line. You could use a surface to divide it. I can't draw it here, but you can imagine if the data is spread out in a volume in a room, if they are divided into two groups, you can draw a plane, not a straight line, but rather a plane between to divide this. And it could be, data could be more than three dimensionals, then we call hyperplane. Okay, hyperplane. But this is a lot more advanced than what we are going to be doing here. But I just wanted to give you a glimpse of how things are going. Now, you guys are all young. For your future, you should be taking a lot of programming classes and statistics and math classes. Trust me on this. The world is changing in a way, it belongs to the smart people. It really does. Okay? World is changing in a way, it belongs to the smart people who know math, science, and they can integrate their knowledge into business. They're the ones. And just think about this. Even 40, 50 years ago, the wealthiest people in the world were people, those who had real estate, okay, or the oil, okay. The richest man, when I was a teenager, the richest man in the world was a guy from Brunei. He was the Sultan of Brunei, or the wealth was among the rich people. It was held among the rich people, like the Trumps of the world. Okay, Trump is a real estate businessman, or at least he claimed, right? But people who inherited the wealth, they're the ones who held on to it, physical asset. If you control the minerals and precious metals, you control wealth. If you control the real estate, you control the wealth. But things have changed. The Mark Zuckerbergs of the world, or the Bill Gates of the world, okay? These people do not come from the very, very, very wealthy families, okay? Or the Google Sergey Brin or Steve Jobs. Steve Jobs, he even was raised at a foster care home. Not foster care home, foster home. He didn't live with his biological parents. He was raised by another family in Cupertino area. These are people, they became the wealthiest people or the most influential people in the world because of their brain. And so it's not because their parents gave it to them, like the Trumps and Saudi or Middle Eastern oil people, okay? It is not inherited. So I want you to think seriously about taking a lot of math, statistics, and programming classes, regardless of what you study, because many of the tasks, and I don't mean to scare you off, many of the tasks that are routine, that you think, oh yeah, I don't care really, I want to have a simple life, I just want to do the regular 8 to 5 job that where I go and do certain things again and again and again. You can be assured many of these jobs won't be in much demand in the future. Let's say, let me give you a simple example of somebody says, okay, I don't want to work. I don't want to go to school as much. I'll be working at a grocery store. I'm okay with it. All right. I'm going to be working at a grocery store, or I'm going to work at a pizza delivery place. I'm okay with it. I love eating pizza and making pizza. You have to think twice. The grocery store checkout jobs might be gone, which already started, self-checkout. And it's going to get more advanced and advanced. Pizza delivery job, let's say, oh yeah, I'm going to work as a pizza delivery man. That would be funny, because very soon pizza will be delivered by self-driving cars, because no human is needed. Robots are going to deliver it to you. So then your job is gone. If your job is gone and you don't have skills, you are out of luck. And the world has no mercy for people, those who don't have skills. That's the reality. I'm telling you the truth. I'm not trying to sugarcoat things. People love you based on your ability to do things. If you don't have any ability or capacity to do things, they won't care. You won't have money, you'll struggle. So very important that you educate yourself. All right. Now let's go ahead and talk about linear regression. Okay. So linear regression, we are trying to find the best fit line. Okay. And the way we do it is this. So I'll just not give you as much information on linear regression today, but I'll give you the most important information that we need. So let's say we are dealing with these data sets, okay? Something that looks like this. This is the data set we are dealing with, all right? Now, we need to find the best fit line through this data set. Now, let's say I ask Alicia, what's the best fit line through this? Alicia says, in my opinion, this is the best fit line. Then I ask, let's say, Araceli, what is the best fit line? She says, no, in my opinion, this is the best fit line. And yet I ask another student, let's say Jerry. Jerry says, in my opinion, the best fit line is this one. Now, which one is the best fit line? It could be very subjective, okay? It could be very Subjective, which one is the best fit line? So to avoid this subjectivity, to avoid this bias, individual biases, we introduce a mathematical way of defining a straight line that best fits this data set. So the way we would do is this. What we are going to do, we are going to draw any line, doesn't matter. Let's say this is a line. Then we are going to, from each of these points, we are going to draw a vertical line on the line. Okay, on this straight line, blue line, we are going to draw vertical lines. So let me use a green color so that you can see. We are going to draw a vertical line from there. Okay. So we are going to draw vertical line from each of these points on this straight line, and then take the length of each of these green lines and square them. Okay. So let's call this one L1, L2, L3, L4. So, okay. And you name them accordingly. So you take length of L1, you square it. You take length of L2, you square it. You take length of L3, you square it. Okay. You square it. Hold on. And you keep doing it for the n data points that you have. You have n data points, Ln square. Okay. And you sum it and you label it by capital L or uppercase L. So there you could draw another line and you can find another sum. Okay. So let's call this for the blue line, let's say L1. Now we will draw another line. For that, we are going to get a sum. We will call it L2. We are going to draw another line. We are going to call it L3. And we can draw as many lines as we want. All right. Remember, this L1, L2, L3 are the sum of the squares. Okay. Sum of the squares of these vertical distances. Sum of the squares of the vertical distances. So if you draw a different line, you'll get different vertical distances. And you square them and you add them. So what you will get is L1, L2, and up to, let's say, Ln. And that n could be any big number you want. And the way we find the best fit line is the minimum of all of these numbers. So look, for each of these L1, L2, L3, there is a corresponding straight line, right? For blue one, we got L1. Let's say we have another one, green one, we'll have L2. Let's say we have another purple line, L3, L4, okay? We can have many, many lines like this. And we take the sum of these for each of these, and we look at these numbers and look at the minimum possible value that we got from all of these. And that minimum value, let's say, for simplicity, let's say that minimum is associated with L1, okay? Now this blue line is the line, we will call it the best fit line or regression line. Regression line. Okay, amongst all the different lines we found, the minimum is achieved by line 1. So L1, okay, line 1 or L1, minimum is achieved by this. So we call this the regression line. And when we are going to be using calculators to find regression line, this is exactly what the calculator is doing inside. It's finding the minimum of sum of the squares. Okay, that's why it is called least square method. Least square method. Okay, this is called least square method. This is one way of finding the best fit line through a data set. There might be another way. Instead of just adding, instead of just squaring and adding the numbers, you could also do something like absolute value of each of these little L1s, okay, plus L1 plus L2 plus dot 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 plus Ln. You can find the absolute value. So that's also another measure that you could use, okay? So these are two different methods that I showed you for finding the best fit line. But this is the most common one that is used in real life, okay? So that's why we are going to be talking about it. That's the least square method, or LSM. That's how you find the regression line. However, you will never ever find it by hand, keep in mind. You'll never find these values by hand. You'll be using a calculator, and the calculator is gonna go ahead and do the calculation, and is gonna give you an equation like y is equal to mx plus b, or we write it as y hat is equal to beta 1 x plus beta 2. Okay, structurally this is the same. Y hat is the predicted value. Okay, y hat is the predicted value for coefficients beta 1 and the constant beta 2. This is like y is equal to mx plus b. I don't know if you realize, suddenly I became too mathematical. Started to talk about a lot of symbols and mathematical equations and this and that. I promise I won't be talking about it for too long. This is as bad as it would get. I know math is not exactly your favorite thing, but soon you'll realize that math is everywhere and math is taking over our lives, okay? And we don't have a choice. Everything will be, many things in life will be revolving around artificial intelligence. Maybe 100 years from now, many of the things will be automated, right? Anytime you're thinking about artificial intelligence, you should be thinking about math. Behind the story, under the hood is math, a lot of mathematics and programming. Okay, I think I'm going to stop here for the day. Any question, anybody? I could answer anything.
No questions.
No questions, everybody okay? All right, folks, thank you so very much. I'll talk to you on Wednesday, and I'll continue with the linear regression examples on Wednesday, and then we'll go from there. Thank you much.
Thank you.